induction. You may have to apply in the assignment which you're supposed to submit it today. Any doubts on that? Or do you have any other doubts apart from induction? So one of the participants says that you were unable to attend the last session. I hope you'll be getting the recording soon. Once you get the recording, just check through it. I'll just give a brief outline of what is said in the last session. Mathematical induction is a technique which you use to prove some statement. So what you have to do is you have to have the statement which you're supposed to prove as P of n, where n is the parameter which related to the statement that you're supposed to prove. Now what you have to do is base case. Base case is nothing but some starting value you can assume and prove that the statement holds. And induction hypothesis is what you assume for n is equal to k. And finally, you have to prove the induction step, prove for n is equal to k plus 1 using the hypothesis. You assume for n is equal to k, and using that, you have to prove for k plus 1. Let me just write it here. For example, if you want to prove that 1 plus 2 plus the simple expression which I used last time is nothing but n into n plus 1 divided by 2. This is nothing but the statement which you're supposed to prove. It depends on n. So I call P of n to be the whole expression. Now base case n is equal to 1. When I substitute n is equal to 1, the whole expression on the left hand side is simplified to 1. The right hand side simplifies to, when you substitute n as 1, what happens to it? You get it as 1. So when you have the base case to be true, you proceed with the induction hypothesis. So what you do in the induction hypothesis is that you will assume for n is equal to k. The case when n is equal to k, you assume the whole statement to be true. So 1 plus 2 plus etc. up to k is equal to k into k plus 1 divided by 2. Now you assume that this is true. This is our assumption. Assume that this is true. And in induction step, which is the last step, you will have to prove for n is equal to k plus 1. So what we do is, for n is equal to k plus 1, what are we supposed to prove? To prove 1 plus 2 plus etc. plus k, the last element would be k plus 1. You have to prove that this is equal to, when it's k plus 1, what is the result? The last element is n, so n into n plus 1 by 2. So here the last element is k plus 1. So k plus 1 into k plus 2 divided by 2. This is what you're supposed to prove. So what we do is, we know that by the previous step, the induction hypothesis, this is assumed to be k into k plus 1 by 2. You have k plus 1 to be added. So simplify, you will end up with this expression. So you assume for n is equal to k, prove for k plus 1. This is nothing but weak induction. And there is another induction called a strong induction, where you assume for all the values from 1 to k. P of 1 is true, P of 2 is true, P of 3 is true, etc. P of k is true. Now using all these assumptions, you prove for k plus 1. So these are the two types of induction. I worked a couple of problems on the mathematical equations, as well as one problem on graph theory. You can just have a look at the recording. Apart from this, do you have any other doubts? And I would like to make one thing clear. Many of you were asking whether you need to register for the exam. There is no registration required. Prasad sir, you have any doubt?
No doubt, madam.
Okay.
Madam, can you discuss any problem from worksheet 2?
Worksheet, like that's supposed to be submitted by tonight. So the next session, next week session, when sir handles the session, sir will be discussing the solution.
Okay. Madam, one more question here is we have every data structure and algorithms has to be demonstrated to the students, like program you have to write and demonstrate. Is it required?
No, sir. Here the course is to just understand how it is done.
Okay.
Programming part is not there. You can visualize. We have given links in the important instructions file, so you can visualize it.
Okay.
The coding
Okay.
part is not. You can try coding it, but this course is mainly to understand the concept.
Yeah. But my question is whether we have to demonstrate to the students. I'm asking. Is it necessary to go for program for every concept we teach or anything?
Uh,
Okay.
So,
Yes, please.
apart from this course, you are asking whether in your place, workplace, you wanted to demonstrate it, or what is that? Is the question that you ask, right?
Yes, 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 ma'am. Yes, correct.
If you wish students would understand by demonstrating, you can definitely proceed with it.
Okay. Thank you.
Welcome, sir. Sir, I don't think they have doubts.
Okay, just a minute. I'll get on with what's coming next week. Yeah.
Yes, sir.
Dev,
I'll stop presenting, sir.
hello.
So there is an echo from your side.
Hello. Okay, still figuring out. Priority queue. Um, So bulk of the course is about this. Then in the last week, I had some miscellaneous topics, suffix trees, something about hashing, red black tree, different B trees and combinations of that. That's pretty much, in my opinion, the core of data structures. Anything beyond is extra, but if you manage to cover these very well, I think you're doing a good job. And so I had some very simple exercises on heaps and search trees. And then what follows now is, I think, I don't know whether it's released already or you'll be released tomorrow or day after, is we are starting on algorithms. So clearly, I did not go deeper into insertions, deletions, and balanced binary search trees because I assume that's something you normally do anyway, and you have to do this core. I'm trying to only tell you how to motivate things and additional things than what you normally do. So you have to continue to do your detailed implementations of insertions and deletions and insert and delete max and all that in the data structures course. So now in algorithms, again, you will see that always in any course, any topic, the first lecture is very important, and you don't want to do definitions, what is an algorithm in Big O, all that kind of thing. If you see my first lectures on algorithms, consistent with whatever we have been talking about, we will start with the problem. Okay, so a very simple problem where given two arrays A and B, of some numbers, find all common entries appearing in both A and B. Okay, so this is the problem. Again, as always, we start with yeah. So the only thing is these two arrays are very, very large arrays. Think of them as Aadhaar numbers or land record, SIM card number, something like that. So tens of billions of numbers. And the problem is very simple. I want to find all entries that appear in both the arrays. Okay. Can somebody give me an algorithm for this? The problem clear? Can somebody give me an algorithm for this? Very, two large arrays. A and B. I want all entries that appear in both A and B. Okay, Ratikanta has a great algorithm. Brute force. Actually, you can unmute and talk. I would like to listen to people. Since it's a small number, there won't be any chaos. Yes. So one algorithm being proposed by Ratikanta Rao is that take two loops, brute force. So you have two for loops. For I going from 1 to n in A, and for j going from 1 to n in B. If AI is equal to bj, then you're going to output that yes, you found something common, maybe store it in some other array. Otherwise, just keep going. Okay. So first of all, if you are teaching this course, this simple problem, make the people come up with this algorithm. Okay, I mean, I always believe in tossing something simple so students can speak up and answer. Okay, so you should wait until somebody comes up with a solution for this, which typically would be like this two for loop solution. Okay, now how much time will that algorithm take? These numbers, two lists are n. If you just run for I going from 1 to n, for j going from 1 to n, and compare AI and
N
bj,
square.
exactly. So that's an n square algorithm. Okay. So this much you should, when you're starting an algorithms course, this is my usual problem, because everybody thinks it's very easy. They're going to come, start, speak up something, come up with this. They can easily analyze it. It's an n square algorithm. Okay. Now we want to improve this. Okay. Well, you know why? In fact, if you please go look at my video, if n is like 10 power 10, I said it's Aadhaar numbers, huge number database. N square is something like, how much is n square? When n is 10 power 10?
100.
Yeah. Yes?
100.
10 power 20, sir.
10 power 20.
I know, I know somebody will say 100.
Ah.
That's why I waited. Right? These are all some tactics when you're teaching. Don't settle for correct answer. Wait for somebody to say, wrong answer, make the class confused whether this is right or wrong, and then people will just interact, right? It won't be monotonous. So n square is actually 10 power 20. So this is what your algorithm will take, because remember our n is very large. Okay. So now if you make the assumption that, how many steps can your modern computer perform in 1 second, number of steps per second is about 10 power 10. Okay, modern computers. They can perform billion instructions in 1 second. So that means how many seconds will this algorithm take? Is the question clear? My algorithm, n square algorithm, n is 10 power 10. So it's like 10 power 20 comparisons it's making. But ideally, I want to know how many seconds, how many minutes, how many hours the algorithm will take. So I want to translate this 10 power 20 steps to number of seconds. And I'm going to make a realistic assumption that 10 power 10 steps you can perform in 1 second. So if I want to perform 10 power 20 steps, how many seconds will it take?
Uh, 10 raised to power 10.
Very nice. Exactly. Here also people will get trapped. People will say 2 seconds, all that kind of thing. Okay. So you will have fun running around the class. So this is actually 10 power 20 by 10 power 10. This is 10 power 10 seconds. So this simple algorithm, brute force to for loop algorithm, on when n is like a billion, right, or even 100 billion, because that's the population of the country, that's the size of the Aadhaar database. So there are 100 billion, that's 10 power 10. Then if you do calculate into seconds, this is 10 power 10 seconds. And if you actually check Google what this means, this is about more than 300 years. Okay, it's mind-boggling. It's very dramatic when n is very large. So where are we? We started with a simple problem, very large n, very simple algorithm, n square algorithm. We ran brute force. Good. N square algorithm. If you do some calculations, go look at the videos and understand carefully what is this calculation. It turns out it takes about 300 years the algorithm will take. Okay, so it's not useful at all. Okay, what can we do to improve it? Well, I don't know. But suppose I tell you B is sorted. Right? Remember, we have these two arrays, A and B. And I say, suppose one of them is actually arranged in increasing order. Now, can you do better? See, what is this n square algorithm doing? For every element in A, it is checking whether it is present in B by doing a linear search. So there are n elements, so n square time. But if B is sorted, what can you do? Can you do better? Right? Again, remember, my algorithm, my problem is I have these two arrays. I want to find all entries common between A and B, but I give you extra information. So B is arranged in increasing order. What can you do? Very nice. More Magesh.
Binary search.
Excellent. So what you can do is for every entry in A, look whether it exists in B by doing a binary search. And we can do it because B is sorted. And binary search is something we have already done in like first lecture, data structures, right? Students would have done this in the previous course on data structures before they come to algorithms. They should have done binary search. They may or may not have done the analysis, but if you have taught them properly, you would have taught them the analysis of the algorithm. So now how much time will this algorithm take? For every entry in A, look for
N log n.
n log n, right? So now it's n log n. With B is sorted. Now let's do the same calculations we did. Remember, n is 10 power 10 log 10 power 10. This is the number of steps. But if I want to convert it into number of seconds, I have to divide by 10 power 10. So this is log 10 power 10 seconds. This is nothing but 10 log 10 seconds. And what is log 10? Remember, log is to the base 2. So what is log 10?
Just about 2.
No, to the log 10 to the base 2. Just about 2 is at
3.
No,
Just about 3. Sorry.
1.
About 3, right? 2 cubed is 8. 2 power 4 is 16. It's something between 3 and 4. So I'm going to say it's even less than 40 seconds. Even if I approximate it by 4, it's 10 into 4, 40 seconds. Same problem. With this additional information that B is sorted, now I can improve from 300 years to 40 seconds. Okay. So what I want you to do is to please go over the videos. I'm just giving you a trailer. They are all there, and understand all these calculations and this problem, and n being large, and see this dramatic difference of how n log n can improve over n square when n is such a large number. Okay, when n is small, these things don't play a big role. So the improvement is not between 5 minutes and 10 seconds, 315 years and 40 seconds. Okay, now this is the dramatic thing you want to say in your first lecture on algorithms, saying, whatever I said is very accessible. Everybody can follow it. Take the simple brute force algorithm. Everybody will come up with it. Look at n square, do the calculations, and then say if B is sorted, you can do binary search, n log n, do the calculations and see that it's 40 seconds. Okay. So you're giving a very important motivation for why algorithms are important, why these kind of asymptotics, n square, n log n, theoretically analyzing these things are very important. And now you are also giving motivation for why sorting is important. Right? Because you could do this binary search because we assumed that my array B is sorted. Now, what if it is not sorted? Well, first sort it and then do this. But how much time does it take to sort? Now it takes us to sorting, right? Naturally, it gives you motivation to sorting. Then you do some simple n square algorithms, insertion sort, selection sort, and then eventually get to merge sort, merging and merge sort, divide and conquer algorithmic technique. How do you analyze merge sort? Well, it's a merge recursive algorithm, so you need to get on to recurrence relation. You need to talk about solution, master theorem, and all that. More examples of divide and conquer. So this, again, the topics what you do are not very different from what I'm saying. You always do them. But the sequence, the motivation. So I'm saying when you start off with this very simple problem, convey this thing about n square and log n, and immediately you can motivate them why sorting is an important problem, because you sort it. Because you can search faster. So then how do you sort? There are multiple sorting algorithms. Talk about insertion sort, selection sort, merge sort. When you get to merge sort, it's divide and conquer, recursive algorithm. You need a recurrence relation solution for them. More examples of divide and conquer, Strasson's algorithm, integer multiplication. You can naturally get into all this. Okay, so these are topics in your course. You might be doing them in a very distributed, unconnected way, but here is a way to just sort of connect them, keep them engaged, motivate them. And that's what my first next week lectures is all about. Exactly, it follows this path. We will do all this divide and conquer. It's a very simple problem sheet on divide and conquer. Okay, so that's what this next week lecture is about. Okay, stop here and ask any questions. Yes, Ratikantam.
Sir, as a student, I always feel difficult in recurrence relation because some relations that are odd type which can't be solved normally, we have to make trees and like that. That always feels difficult, sir.
Yeah, it is difficult. I have given in the video some ways of how you can solve. So even binary search, how do you solve? By simply unwinding this recurrence, right? What is a recursive algorithm? It's applying the same algorithm on a smaller input. Keep applying it until it becomes a small number. Then you don't apply recursion, you solve it. Then how you analyze it? You will write a recurrence relation, keep expanding the recurrence relation by applying the same recurrence again and again, and then finally you will have some summation and you will solve it. Okay, so that's how it is. You'll see the videos, look at some of the ways I've given, and then we can come back and discuss more questions next time if you have.
Yes, thank you, sir.
Yeah, but the main thing I want to say is this sequence, right? Why do we have recurrence? Sometimes, often I find they do recurrence relation completely separated from recursive algorithms. Recurrence relation will be independently taught, master theorem, whatever, all that. But you have no idea why they are important. And then when you do merge sort or binary search, people don't analyze it properly. And the whole point of recurrence relation is for analyzing those algorithms. So you need to do these connections. And that's what I'm trying to establish here, that motivation, keep them engaged. You know, simple sorting algorithms which you can come up with in your high school, right? Again, remember, sorting is something people have done in high school. Arrange it in increasing order, decreasing order, except they have not done it for 10 million numbers. They will do it for 7 numbers, 10 numbers. When you are talking about 10,000 numbers, you need to capture the algorithm, write a program for it, and analyze it. And you immediately see that the simple algorithms you've seen are n square, but with a very simple divide and conquer, you sort this half, and merge gives you an improved algorithm. How do you argue it is improved? You have to analyze it. How do you analyze it? Write a recurrence relation, use some theorem to solve the recurrence relation, analyze it, then see that it's n log n. And then you do more examples of divide and conquer. And if you see, I have given some problem sheets. For example, Strawson's algorithm is a pure magic. How he managed to improve from 8 multiplications to 7 multiplications is a magic. You don't delve deeper into that in your class or in your exam question paper. It's, for example, I have seen questions where people have asked, how does, what are the 7 multiplications in Strawson's algorithm? Oh, that's just criminal. That's not something you will ask. But I have given you some example problems which test their understanding of Strawson's algorithm and the recurrences without needing to remember those gigantic equations. Okay, so that's also something you will see it. Yeah. Okay, so that's what's coming, and next week we can, you look at the videos and we'll see more of this as well as the solution for the second problem sheet if you have it, because we don't want to discuss it because it's, some people may be still submitting it later today, and the deadline is today. Yeah. Right. Okay. Any other questions, comments? So is Kitna there? I hope she is, but I don't know when the next videos will be released. So I suggested releasing them today, but maybe tomorrow or Monday. Okay. Any questions? Let's see the chat. Yeah. Okay. So take a look at the videos and we can come back and discuss more questions next week. Okay. There are no more questions. We'll stop here then. Okay. Thank you then. See you next week.
Thank you, sir. Thank you,
Good
sir.
night, sir.
Good night.